How close do I have to be? Like,
just stay there. Perfectly. So, struggling with the room light again. Good evening. The last talk for today will be Jasper-Nance, shooting at things, or shooting things.
Parts, though.
Oh, there's two parts. Okay, we'll see.
Okay, hi. I'm going to be giving a two-part talk. The first will be over high-speed photography, and then the second half is over Heatsink Labs, which is the Arizona hackerspace scanning electron microscope project, where we're attempting to build one from scratch. So starting off, the type of high-speed photography that we do is not, people are always like, oh, can you get video from that? So I just wanted to lay out exactly what goes on with this specific type, which I like to call a shot in the dark. So guns are like fun because you get dramatic, kinetic photographs. They're very aesthetically pleasing. So you probably should do this safely, meaning out in the middle of the desert, middle of nowhere. And well, you're excited, right? Because you've got like fun stuff and you've got a gun, and that's cool. And you probably brought something to shoot, like an apple, right? That's like the famous high-speed photograph shot is Edgerton's shot of the apple with the rifle bullet going through it. And then, of course, we want to be a little bit respectful of the environment. We might be shooting glass or computer monitors, something, so we should probably put down a tarp. We don't really want to hurt the animals in the desert. And then, of course, we need a camera. And here I've shown this giant shutter release cord, but I don't actually use that. It's just fun to draw. The flash itself is a very specific type of flash that I will get to later that's connected to a microcontroller. And then to this microcontroller interfaced multiple types of sensors, because obviously you have to synchronize when to take the picture to the event that's occurring. So one of the first ones that was done historically was to use a microphone, which is here, but I didn't like to use a microphone. It's too analog and messy. So the first one that I came up with was to use a laser pointer and just shine it directly onto a photodiode, and then whenever something breaks the laser, it takes the picture. You can also use a chronometer, which times the projectile and makes a determination on, okay, well, it took this long to go from point A to point B, so it'll take this long to go to point C, delay, and then trigger the flash. And then, of course, you have to dim, it's nighttime, right, because there's a moon, and you have to dim the little lights you're using, fire the gun, goes through the apple, breaks the laser beam, takes the photo. So this is my version of the Edgerton photograph. This is a hollow point bullet instead of a rifle bullet, so you can see there's a dramatic difference in the reaction of the subject. Here's a picture of the actual setup. There's a banana here. There's a 380 ACP bullet here. There's the muzzle blast from the gun here. You can kind of see my face ghosted out right here. It may be difficult on the screen. There's some flashlights of people who were walking around prior to the shot. The high-speed flash is sitting on this table. There's a camera back here, and then down here and up here are the lasers that were shining diagonally across in front of the banana. One of the great things about this type of flash over, say, building a very specific type of camera with a high shutter speed, or using a, like a video camera, like one of the Phantom Flexes, is that because the flash is taking the photo and the camera is not coupled to the flash in any way, you can get this same shot from multiple angles, as many as you have cameras. So this is from the front. Here's the banana, and you can see we actually grazed the front. Here's the same shot from the back. You can actually get a little more information about what happened from these two. From here, it looks like it may have gone through the center of the banana, and it's very clear it did not. So building one of these special flashes includes high voltage, which is not really a problem because when I was 15, I built my first Tesla coil. So being like a Tesla kid, I have no problem with high voltage. In fact, I love it. Custom flashes, also no problem. I've done custom flashes for microscopy to freeze the cilia on rotifers or paramecia shown here that I took. I've also done some camera trap work where you leave a camera in the wilderness for days, weeks, however long. And the goal there was to make this thing last literally as long as possible. So it ran off a giant deep cycle car battery, and I just made it from scratch using the largest flash bulb I could find on DigiKey. And then you put all these together at last, and you get the triggered spark gap. This is an 18,000 volt arc between two electrodes on the outside of a quartz surface with a trigger electrode in the center. It's characterized here. It's a lot like a MOSFET, specifically a silicon on insulator MOSFET, if you're familiar with that technology. If not, not a big deal. Basically, you have an insulator on which the two electrodes are placed. One is at a very high potential, and the other is very low potential. You want to space the two so that the space is just greater than the breakdown voltage. In practice, you actually want to add a little bit more margin because humidity in the air or ionizing events such as the flash from other cameras can actually ionize the air enough or provide conductivity along this glass surface so that the capacitor will discharge prematurely. So it's actually kind of a frustration because in Arizona, it is very dry. And so you can set up the flash bulb in one way. And then you take it to New York for a commercial photo shoot where it's very wet and everything breaks. Not that I'm speaking from experience or anything. So you trigger the electrode on the other side of the glass with a 50,000 volt pulse. Doesn't need to be a lot of energy. It just needs to be a high voltage for a very short duration of time. That charges the glass plate as if it were a capacitor and ionizes the glass, either plus or minus. The polarity really isn't important. And this allows a conductive path for a spark to form between the two electrodes. The flash duration is, these are two plots for two different capacitors. One is some very cheap rolled, I think they were Lithuanian capacitors. A huge bank of them. You might be familiar with making these for Tesla coils where you use like just a buttload of tiny caps instead of shelling money out for one giant cap. The second green trace was actually a Maxwell pulse cap, and I was very surprised to see that the inductance of the rolled cap was not the limiting factor of the flash duration. It's difficult to see the graphs, the units, and I apologize, but the peak lasts for about a half a microsecond, and then the decay lasts for about 3 to 4. The air glow is dim, but it is present. So if you have brightly lit details, they're probably going to show up very sharply, but if you have specular highlights in the photograph, shininess, anything like that, you might see some streaking, and it actually tends to be slightly reddish because the air glow is slightly reddish. And then I just showed the schematic for the flash duration measurement, which was actually more complicated than I thought it would be to get a high-speed diode and to bias it correctly with impedance-matched lines. Turned out that it was more of an exercise in measurement equipment setup than I intended it to be. Here's a table for the different types of flash durations that you need to capture different events. So just for note, your standard off-the-shelf flash unit will probably be around 4 to 8 milliseconds, and it's done on purpose. They actually stretch it out with an inductor to limit the instantaneous current flow through the xenon bulb, which obviously makes the xenon bulb last longer before it cracks. And then also xenon has a very long air glow, so even if you did have a short pulse, xenon isn't particularly useful. To get a butterfly, I'll admit, I kind of pulled these numbers out. The butterfly, I thought, well, it moves at, a quarter of a meter a second. So that's 1/250th of a second. You could get that without a flash on a normal camera. A housefly moving at 2 meters per second is 1/2000th. Still, you could get that in a brightly lit room with a normal camera. A sparrow moving at 10 meters per second, all of a sudden we need 1/10,000th. Hummingbird wings moving at 33 meters per second, we're talking 1/33,000th, and up to bullets where we need about 1/1,000,000th of a second. So the half microsecond duration of this flash is actually good for 1/2,000,000th of a second. And this is for 0.1 millimeter blur. This is sort of an arbitrary unit. I thought, well, what makes a picture sharp? What makes a picture blurry? I do a lot of macro photography, so 0.1 millimeter is probably, for an extreme close-up of a bullet, you're gonna notice if it's greater than that. And then, of course, high explosives are up at 1/5,000,000th, so capturing high explosives would require a slight modification to this type of flash. Here's a very confusing schematic that I drew by hand when somebody asked me how this circuit works, but I won't let you decode that. I actually came up with a little diagram. So the two separate circuits inside the flash. One charges the high voltage capacitor. It's just a very simple 555 timer going into a flyback from a CRT television, and then charges a 50 nanofarad pulse cap. The trigger circuit is, once again, a 555 going to a flyback, but it's not actually a CRT flyback. It's just a little switching transformer that I probably pulled out of a VCR or a switching power supply, and it only takes it up to about 400 volts. And so I charge a little capacitor at 400 volts, and then there's a triac that discharges that into the primary of a CRT flyback. So whereas normally you'd get 10 to 25 kV out of a flyback, you can actually get 50 kV for a very short amount of time, and that is for the trigger electrode. Here's the circuit board showing the very old school CRT flyback that I was using for the trigger, and it turns out that 50 kV can actually leap quite a distance, and I had to basically pot the whole thing in hot glue, which worked for a time, and then I switched to RTV, which was a more permanent solution. Here it's hot glue, but I should have just stuck the whole thing in RTV. It would have saved me a lot of headaches. And then to the left is a power MOSFET that switches the supply into the flyback. And actually, it does require a car battery to work. You can't get enough current out of a switch mode power supply. Even a PC power supply, it just does not like, it trips the overcurrent protection. So I usually use a lead acid deep cycle battery to run the high voltage. And I have since popped it from 18,000 volts to 30,000 volts to fully charge the Maxwell pulse cap I'm using. And here's the finished product. And I say that in quotes because, well, first of all, it's probably never going to be finished because I'm always tweaking it. And second of all, I haven't actually painted it my favorite color, which is purple, in these pictures. On the right-hand side, you can see it with the case taken off. There's just the reflector with the flash in it, and the pulse cap sitting behind it, and then the control circuitry inside this ruggedized box to protect against banana splatter, which I'm just going to tell you gets kind of everywhere. To trigger the camera, I have these little RF camera triggers that I built. It's just an MSP430 and a CC1101 and some buttons. It's got 4 outputs, but honestly, this has proved to be very flexible because you can use it for kite aerial photography, and if you end up putting a power amplifier on the transmitter, you can actually use it for near space photography. So these are some of the other uses that I have. And that's from, I think, 91,000 feet over the northern United States. Here's the laser that I use. There's a photodiode on the left and a laser on the right. First, I started out with a 5 milliwatt red laser, just because it was like, hey, I've got one on my desk. Let me cut it off and add wires. Okay, done. And then it started doing this, where it's like, oh, that's cool, there's a laser. And then people start asking questions like, oh my gosh, you blew up a beer with a laser, that's so cool. Like, no, I didn't actually blow up, no, okay. So then, you Photoshop that out or whatever, and then you're like, you feel guilty and you can't sleep at night because you're Photoshopping what's supposed to be objective, scientific photos, and then, really you just order a 300 watt infrared diode on eBay, dial it down to about 100 milliwatts, and you can actually see an 808 nanometer laser spot in the dark to a dark adapted eye. But I'm not going to say that that's really safe because that's a lot of milliwatts, and I'm fine, but I mean, don't do this at home maybe, I guess. The pros of the laser is that it's very precise. You can say, I want the bullet to be here, I want the explosion wave to be exactly here, I want X, Y, Z. The cons are that it's precise. Can you actually shoot the bullet there? Because I suck. Like, my aim is just awful. And then there's noise. The photodiode, you want to dim the thing as much as possible so it doesn't show up in the photo or blind people, which means you run up to the sensitivity of your detector. And then noise from this 30,000 volt RF power supply is just spilling across the spectrum, creating false triggers. It's very frustrating. And then laser splash in the photos. The other thing is that it's a laser. It's very precise. You're out in the desert with these tripods on dirt. If the wind blows or it's dark, right? So you're out there with 15, 20 other people from the hackerspace. Everybody's got targets, ideas. Everyone's excited, trying to set up their camera. Everyone's kicking and bumping the tripod every 5 minutes. You have to realize, oh my gosh, you just want to pull your hair out at some point. So these following pictures were taken with, there's also an infrared beam that I used. It's a television receiver, a 44 kilohertz demodulation, and then a 44 kilohertz strobed infrared LED. And this does not work for high-speed photography, such as bullets, but it does consume less power, is less tricky to set up. You can hike around with it. I put it in my backpack, and I used it for camera traps. And it actually works really well for things like bugs, because bugs don't move very fast, but you still might want to precisely position them. Or my cats, because I don't really want my cat near a high voltage source, really, or lasers. I don't want to hit his eye, but I can trigger a normal low speed flash with this whole setup too, and he's just, he's a good beta tester. So here's the insides of the controller that I'm using. It's an Altoids tin with an MSP430 chip, one of the old style JTAG ones. And it's got these dip switches to set make or break mode, laser microphone mode, and then wildlife or high speed mode, where wildlife mode does a lot more filtering to make sure there's really an object there before it just starts flashing endlessly. And it only allows certain amounts of photos within a given time, because if a bear knocks over your laser, you don't want it to just take a billion photos of nothing. Now the challenges in the software kind of evolved over time to frustration with laser spill, really. So there's an implemented like laser turn off, so that the second it triggers the flash, it turns the laser off. That keeps explosions and mist and just crap that's flowing through the beam from showing up. Like in that beer bottle one, really what set that laser beam so visible was the beer. It turned into a fine mist, it went everywhere, and it very brightly exposed the laser beam. Turning it off helped a lot. But then what happens is you have that RF, and you just fired a big pulse of EMF. So the MSP430 resets, and then your laser turns back on, and then you're back to square one. So I had a turn-on delay, which kind of helped, but then how do you align the laser? It became a very frustrating exercise, so I came up with an arm mode. So there's a button, and there's a little LED, and the LED indicates whether the laser is actually striking the detector correctly. Then once you get everything set up, and you're ready to turn on the high voltage, you turn on the high voltage, then you can press the arm mode, and then it will take the one beam break, turn off, trigger flash sequence, and that saves a lot of headache. Here's an egg with an air rifle. This was probably one of the very first photos I took with this setup, with the high speed working. There's a banana and a 22. You can see there's laser splash on the banana. The best thing you can do with a Pabst Blue Ribbon, honestly. Here's an apple and some magic pixie dust. The apple, you can actually see the silhouette from the laser splash inside the blast radius. Grapefruit and more of that pixie dust. The neat thing is you can actually see the internal structure of the grapefruit. Those striations would be the slices, right, that you can pull apart. There's a higher density or slightly different characteristics, so the shock wave travels through it slightly different. And of course an iPod, which I just want to say that if you do this in your garage like I did, you might take out just about every piece of equipment in there with pieces of the iPod. That was a lesson learned. I'm glad that none of the cameras were hurt, but every single piece of equipment was just decimated.
How long does it take to reload the capacitors?
The capacitor charges in about 5 to 10 seconds. It'll fire anywhere between probably 80% and 100%. The limiting value is actually the trigger circuit. I have a trickle charging that 400 volt capacitor because I didn't want to draw a lot of power in that circuit. So the TRIAC fires that capacitor in serial. Actually, I can go back to that schematic. That's going to be difficult to read, but the trigger circuit actually took me a long time to work because there's a lot of noise going through, and so here the trigger circuit, there's a capacitor here that's charged to 400 volts, and the TRIAC discharges it serially through this cap. That limits the amount of energy that can go into this because I had problems with the TRIAC burning out constantly because I'm dumping a lot of energy very quickly. And just sizing that capacitor was a rough measurement, but I had to discharge it through another capacitor just to get a very tiny pulse. The TRIAC just kept burning out, and then I kept getting arcing internally to that area, and it was very frustrating. It kept also burning out the BJTs that trigger the TRIAC, so I had to size that so that just a very, very tiny pulse made it through, but then that cap is, of course, charged. So it takes probably about 10 seconds to discharge so that you can fire it again. So that's really the limitation. That's actually good because setup takes a heck of a lot longer than 10 seconds, right? So, but at the same time, you can't really fire this thing bam, bam, bam within microsecond period. You would really have to build multiple units and then trigger them sequentially if you wanted to do some sort of multiple exposure. But then, of course, you're going to have all the exposures on one frame, right? Because now you're talking high shutter speed if you want to do like a video or multiple frames. But it still looks kind of cool if you have an isolated item on a black background. If the item's moving or reacting, you can get some cool photos. I have not done that just because I have not built more than one flash unit, but Alan Saylor, who also does this type of photography, has played around with that idea, and it actually looks very impressive. Here's a wine glass, which actually is grape juice because wine was too good to waste, and a 380 ACP. And I learned my lesson about using grape juice because there's a lot of sugar in grape juice, and my camera buttons didn't work correctly for like a month. And I was very sticky. Mountain Dew, the bullet is actually just out of frame. From another angle, somebody actually captured the AK-47 bullet, but I just like the aestheticness of this picture by itself without the bullet in the frame, though I do usually like to show the bullet. Here's another apple, but a different kind of hollow point, which reacted very differently. Some unexpected things. We tried to make our own ballistics gel out of agar, and it didn't exactly work the same way as gelatin-based gel, but one of the things we noticed is these bullets are always spinning. You never really, at least I don't know that much about bullets and guns and ballistics and all that stuff, and so I was at least very surprised to see that these rifle bullets were tumbling constantly, and later I learned they're actually designed to do that, which is kind of a gruesome thought, but then of course you get bored, right? You're like, oh, I shot an apple like 10 times. Ooh, well, what happens if I put a Q-tip in the air rifle? Well, it turns out it goes supersonic, and you can shoot a Tums antacid, and you can do this in your home, and you don't have to drive all the way out to the desert. And then I started mixing speeds of flashes together. So there's the high-speed flash from one side, and then it's backlit with a normal, probably about 100 microsecond duration flash. So you get this like, this is exactly how it reacted, but then this is where the pieces all went. You get this sort of fluid motion, and this is an idea that I really need to play with more. I haven't done much of it since this photo. So then, fed up with the frustrations of the laser pointer method, specifically when dealing with large amounts of people with our hackerspace in the desert, it just became this just frustration, and I was like at my wit's end by midnight. We were going home when really we should have spent all night getting great photos. So I decided to build the chronometer-based high-speed photography trigger, affectionately known as the chrono trigger. And of course there's chrono, which I felt like obligated to laser engrave on the box. And it's just a tunnel flooded with infrared radiation from these LEDs. And 2 photo gates are along the bottom. They're here and here. And when the bullets pass the photo gates create a pulse. There's a MSP430 in this box. It's actually one of the Easy 430 CC2500s, and it has a wireless transmitter inside there. So on my laptop, I can actually program the specifics, and it actually gives me a chronometer reading. So if you use it in broad daylight, it'll just give you the feet per second of whatever projectile. You could throw a rock through it, you could shoot a bullet through it, it's going to tell you how fast that object was moving just passively. Or I can set it to a mode where it's actually going to activate the flash, and you give it a distance in millimeters, and there's this, it's hard to see, but there's a tape measure that's taped to the end of it here. And you stretch out the tape measure, you say, okay, well, it's 26 centimeters to my target, but actually I wanted exiting the target, so let's set it to 28 centimeters or whatever, and it will calculate automatically, okay, well, it took this long to pass here, this is the velocity, it starts a timer, and then on the falling edge of that timer, when it hits the pre-programmed capture compare register, it fires the flash. And the neat thing about this is that it doesn't have to be precise. It doesn't matter if you throw like a rock or shoot a bow and arrow or shoot an AK-47. It's going to trigger right where you want it to. And some of the first tests, this is kind of how it's set up. The chrono trigger is here. There's a sucker dangling here. Here's the flash. And here's some of the cameras. The air gun is behind Joyce here. Here's a view down the barrel. That's actually a peep in this one. This is one of our high-speed nights at the hackerspace that we did with air rifles inside. And then here's the resulting photo of the sucker where it's very precise. The timing is very precise. We can place a projectile just about exactly where we want it. So it's currently inside the sucker in this photo. Here's some more test runs as a Cheeto crayon. We were kind of like, what can we shoot around here? Oh, look, a Cheeto. It was in the couch. It was kind of fun. Then we went out to the desert, and here's the tape measure laid down alongside as a calibration shot. There's a golf tee and a .22 long rifle. I kind of forgot to list the velocities, but the neat thing is you also get velocity information, so you can use that to debug the flash and say, like, well, is my duration changing? Is humidity affecting the flash? Is something wrong with the flash circuitry? Is not charging the right voltage? And then, of course, here's a Mosin-Nagant round striking a golf tee. It also enables you to do some things you can't do with the laser trigger. You might be able to do this with the microphone trigger, but then you have to make some basic assumptions about the velocity of the bullet, about the velocity of the sound waves, right? I just hate microphone triggers. They're just not precise enough for my nature. So here is an Arizona flag, and the newspaper wanted to do a piece on Arizona guns, and it's a very controversial subject. I really have no stance on guns. I use them to make pretty pictures, but before this, I didn't own any, and now I find myself with a few, and it's like, do I want these? But there's a .22 bullet, but how would you set this up with the laser? Well, you might be able to place the laser vertically, but that you're kind of hoping you can aim correctly, which, what if it skimmed the other side? Or what if the paper buckled like it did? Or, well, then the laser's going to show up in the picture if you skim the paper. There's all these things that you can do with the chronometer that you can't do with the laser, but then, of course, when you're working with massive wet targets, now you have to make some assumptions, well, how much is this trip through this gallon jug going to slow down the projectile because the chronometer assumes constant velocity. So, there's some pros and cons to each. Here's a creamer from your coffee. And then, of course, another challenge with high-speed photography is what looks good. What's it going to do? What happens if, I don't know, like no one knows. Sometimes you picture in your head, oh, it's going to react like this. And then you get the picture and you're like, it looks like someone hot glued a bullet to a green army guy. Like, it's neat, but only if you know the background, right? So you're like, it's not quite what we had in mind. Here's another one where I was trying to take one of the ehsm poster shots, and I mean, it's so cool. You're skimming, it's taking out the capacitors as it goes, but it's not really a good poster shot, right? And then, of course, the one that worked actually was a mistake. There was a software bug, a glitch somewhere. The timer got, the clock speed on the timer got messed up. It happens occasionally from the EMI. So the bullet is actually twice as far as it should be away from the target. So it's about 8 inches to the left. But the neat thing is these bullets spin. So it kind of hit the circuit board, started spinning, just kind of threw stuff everywhere, and it makes a great shot. So there's always these accidental like, oh, that's not what I meant, but you know what? That's actually pretty cool. Kind of the opposite of, I want this. Oh, that looks dumb. And here's one of the pictures of the setups out in the desert. So if there's any questions specifically about the high-speed photography stuff.
So last talk of EHSM was destroying things. After the last 3 days was building things. So are there questions on destroying things and taking pictures of that?
No, I mean, yes, I've been shocked a lot in my life, but not specifically by this setup, because this would probably kill you. It's not really much to joke around with. So I usually keep a grounded strap dangling from the unit, and if you ever need to do any work on it, you can just grab the grounded strap and just kind of throw it at the terminals. Pop. I guess the trigger is always the one that shocks you. It's always the little 0.1 400 volt that you never look at until you touch, and then it burns your finger.
How much faster is your setup than a regular camera flash?
I think the majority of the cost was the capacitor, the pulse cap, about $70 on eBay. All the electronics were scavenged from broken TVs and VCRs. The rest of it was either laser cut out of plywood at the hackerspace or crappily cut out of wood at my house. trying to think of any more expensive parts. The tube, actually, that it's inside is, I found if you made it out of glass, you could get about 10 to 20 shots and the glass would etch and it would actually shatter. So I bought a rod of quartz and I ended up having to buy an entire meter of quartz for some ridiculous price and only using, like 10 centimeters of it, but that's still, it was like 40 bucks for the whole meter and I cut a little off, so it was very cheap. I'd really put no money into this at all.
The question was the pulse duration of your setup compared to like a regular camera flash.
I'm sorry. The pulse duration is half a microsecond, and then a normal, I had some graphs that I was going to put in here. A normal flash is about 4 to 8 milliseconds on full power. As you dial the power down, some flashes allow you to manually set the power. If you take the power all the way down, the lowest that I ever found was 100 microseconds. At one point in time, I actually unsoldered the capacitor and just used the ionization pulse. It's very dim. It would not be useful, but I just wanted to see. The ionization pulse alone was 15 microseconds. So, xenon is just not really the ideal media for the high-speed flash.
So I don't know about the timing for this, but maybe a photography idea, what I would think would be cool to see, would be to charge up a high voltage capacitor and try to use a bullet to trigger a spark gap. Maybe that might make a cool photo.
Yeah, it's true. That actually could be pretty cool. Come out to the desert with us. We're only in Arizona. It's not like it's far or anything. But these are the ideas. This is why I love doing this as part of a community, as part of the hackerspace, because everybody comes with these unique ideas that I'd never thought of before. And it's like, well, yeah, I could go do it by myself and just be grouchy, or do it in a group and come up with amazing, cool ideas that really inspire.
Are you using any special type of xenon bulb? Because I already tried to hook up a high voltage power supply, 20 kilovolts, to a normal xenon flash bulb from a camera, and it just arcs over the flash tube. Right. So do you have to modify the flash tube, or your special type to prevent this continuous arcing and have only one flash from the capacitor discharge?
Well, the flash tube is not a xenon. It's just a glass rod with wires on the outside of it.
So you arc in air?
The air is actually where the arc is forming. Correct. There's no xenon.
There's one more.
If you or somebody you knew were a glass blower and had access to neon equipment and vacuum pullers and stuff like that, what would you choose to make a flash tube out of? Or is this the best? Is the air gap?
Well, I actually do glass blowing. I made this pendant, but I do not have access to neon stuff. I do have access to vacuum stuff. Really, I've thought about it, but this setup works pretty good. The one thing that Edgerton worked with, he was like the father of high-speed photography, is air really is the best. Nitrogen may be slightly better because the oxygen, I believe, is what glows afterwards. Nitrogen may be better. The problem is as I've tried to contain this unit, there's so much energy and so much thermal expansion that it just shatters any envelope that's completely contained. Now, whether or not having a massive tail of gas, a reservoir behind to take up the shockwave would help or not, I'm not sure. But one of the things that Edgerton did is he put instead of using a tube that's round, he used, it's hard to describe, but like a furrow that the electrodes set in so that the glass wrapped around the arc and pulled the heat away from the arc faster. So that instead of just the bottom of the arc touching the glass, the entire arc was touching the glass with the exception of the very top part. So it sat in like a trough. And supposedly that helps to pull the heat out and cool it down quickly, but he was only able to get slight performance increase. We're not talking order of magnitude or anything. For that, you need to change the way that the thing is discharging. Mostly it's the inductance of the leads that's taking it, from the capacitor to the flash bulb. It's that inductance that's ringing that's causing the delay.
And I have to apologize. Of course, this is not the last talk of this day. I'm pretty tired, sorry. Because there is a second part of your talk.
Hi, I'm wondering if you've taken photos of things, any process that has been repeatable, so that you can take the same shot several times in different stages of the process.
It's an idea that I've tried, and I think I just lack patience, and I'm too easily distracted. Yeah, that's pretty much it's certainly possible, and it would be really cool to have a rigid setup where you could, buy 10 suckers and then change the, increment of where the chronometer is triggering by 1 millimeter every time and just get this sequence of events. I've certainly thought of that. Another thing is getting 10 of the same camera, just wrapping them around matrix style and doing a three-dimensional transform. And if anybody would love to help me with that, I'd love to see you in the desert.
Okay, there's one last RSC question. I didn't quite understand. Does she turn off the laser once triggered? That should eliminate the unwanted illumination.
It does and it doesn't. It helps a lot. But at the same time, it's a very long exposure, right? Because you turn off the lights, you turn on bulb mode on the camera, you open the shutter, and while the shutter's open, you have to aim and you have to say your prayers or whatever, and it can be a process of several seconds while you're I don't know, for me aiming is stressful. I start to freak out a little because it's very heavy, the gun's heavy, I can't hold it still, and I'm always wanting to get the perfect photo, and during those seconds of exposure, any tiny dim stray reflection of the laser or the optics, the cheap laser pointers, they don't make a dot, they kind of throw some bits all over, those are just building up in the exposure. So it does help, but it doesn't eliminate laser splash.
Okay, and I think we should continue with the second part of your talk.
The second talk that I would like to do is on a community scanning electron microscope. Okay. So this is a HeatSink Labs community project, and HeatSink Labs is located in Phoenix, Arizona. This is our storefront right here. Inside, there are people hacking at all hours of the day and night, doing multiple projects from laser cutting to milling and machining to 3D printing and hackathons, all just anything. We do everything here. And one day we were doing what we do at the lab, like a normal day at the lab. Normal day at the lab. And, we got a little bored and we started talking about, somehow got on the topic of vacuum systems and SEMs and how crazy cool it would be to have one. And some other hackerspace had one that they got for cheap somewhere, but it just sits there as a table. And, Will Bradley and I started filling up a whiteboard. And we thought hey, actually we could do this. Why don't we? Why don't we do this? I don't know. Let's do it. Let's do it. So we thought of doing it. And we thought, okay, well, an SCM is really just a glorified CRT. You just take your CRT and you tip it over, you stick a bug in it, and you've got it, right? Well, okay, it's a little more complicated than that. Here's an SCM. What makes it more complicated is that the dot size has to be so tiny, so you have multiple lenses. It's just like the difference between a magnifying glass and a compound microscope. Yes, you can call a magnifying glass a type of microscope, but can you get, micrometer resolution out of it? Probably not. You probably need better optics, more of them, collimation, condensers, stuff like that. The same thing with an SEM. But the neat thing is you can start somewhere. If you can start with a single lens design, you can start with a CRT design, you can just add lenses in as you go, and you can add stigmators, and so you can start with a very low resolution system. You can say, look, a penny is round, oh my gosh. And then you can work from there, and it's very exciting. So I'm going to go over a little bit of theory on how an SEM works. An SEM shoots a beam of electrons onto a tiny dot and then rasterizes that dot across the surface of your sample. And what happens when a beam of 5 to 20 keV strikes matter is you get these, this is not a complete table of interactions, but these are the most commonly analyzed interactions. You get backscatter electrons, and backscatter electrons contain the same kinetic energy as the incoming beam. They simply get tugged around by the nucleus of a high Z atom and flung right back out. So these contain information about atomic number. Heavy metals will show up very dark. Things like lighter elements won't show up as dark. Then you've got Auger electrons, which contain information about the energy within the electron valence gaps. This happens when an electron knocks an inner shell electron out, and the outer shell electron falls back down. Sometimes it emits a photon, but sometimes it knocks out one of the other electrons and ionizes the atom. And then these are from 100 electron volts to 500 electron volts, sometimes up to 2,000 electron volts, depending on your source. And you can actually gain information about the chemical composition and molecular bonds and such. Then there's secondary electrons, which are just electrons that get just pew, 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 pew. So one high energy electron comes in, hits an electron, knocks it out, hits another one, knocks it out, that one knocks it out. You get this cascade of very large amounts of electrons just being kind of popped out of the sample. And the interaction depth is very deep for these secondary electrons because the back of the beam is penetrating that deep, but they're such low energy, they're between the work function of the metal and 50 electron volts that most of them are captured by the sample again. They just get recaptured by a neighboring atom. And only the ones from the top 10 angstroms make it out of the sample, the ones that exceed the work function of the metal and manage to, avoid their neighbors enough to make it out into the free vacuum, make it out. So this is a very high resolution signal because it's the top 10 angstroms by the beam width. Of course, you also get X-rays from within the sample, and you can do spectroscopy on those and get information about elements as well. The secondary electrons contain topographical information because of that 10 angstroms. If you can imagine on the left here, we have a fully buried beam profile and a very flat surface. Well, you're only going to see emission from that top ring spot area. And so you're going to get, some. Then if you can imagine an angled surface where the beam is highly incident, more of the side of that buried profile is going to be within 10 angstroms of the surface, so you'll get a larger signal coming from a slanted surface. And you can imagine something like a hair or a whisker or some sort of large protrusion. Well, the entire buried profile is going to be visible along the sides. It's going to be a very large signal. So one of the neat things about secondary electrons is that unlike a normal microscope, like a light microscope where tiny details are more difficult to see, if you've ever tried to look at, the hair on an ant or a bug, or they're tiny, wispy, they're see-through, you can't really see them very clearly, but the larger structures are more visible. It's kind of the opposite effect. The more tiny and wispy and topographically complex the surface, the brighter it shows in secondary electrons, and that's really where you get pictures like this, which is not my picture, it's from Wikipedia, but you can tell that the spiky surfaces of these pollen grains show very brightly in secondary electron emissions, and the surfaces that are just very flat and parallel to the beam don't show, they're very dark. There's a difference between backscatter and secondary. The backscatter, these are some image from Wikipedia, I can't remember what it is, but it's not really important. It's just these dots are very high Z inclusions in the material that are somewhat deep, several microns deep. Whereas at the bottom, you just see the surface texture. So, depending on what you're trying to image, are you trying to impress people with ant faces, or are you trying to do some sort of, forensic study on a material? Depends on which signal you want to look at. So some of the goals that we chose for this hackerspace project are to be empowered and demystify technology. There's that inherent, geek sort of drool that happens when you see something that's like magic, like, CERN. You're like, the Large Hadron Collider, it's like this amazing thing and it's magic and oh my gosh, drool. And that's cool and that's well, but really, it's important to realize that all technology is accessible and all technology is based in reality. And it's something that is within our grasp, whether we choose to say, that's too hard for me, I can't do it, or yeah, let's bring it on, take it on. It's all about your attitude, right? So empowering people to realize, we can build a scanning electron microscope. We can build these things that people tell us, oh, that's crazy, that's smart people stuff. No, it's just reality and it's just manipulating your environment and you can do it. You just got to try. That's very important to me. I think that the hackerspace movement in general is very important to empowering people. So why not have as a central or a project within our hackerspace something that can just empower everybody who walks in the space? Educational outreach is also, a passion of mine. We can bring in high school students, Girl Scout troops, these people who come in and, want to learn. And it's like, oh, well, you want to learn? Well, I can't think of a better way to learn than such a massive project. And then we can build a better community. And what I mean by that is people say, oh, I have experience in vacuum systems. Oh, I have experience in TIG welding vacuum systems. I have experience in machining. I have experience in software, human interface. And I saw your project, and so I decided to stop by the hackerspace. And actually, I saw this 3D printer over here. They stick around. and they see these projects we're doing. And so we get a more diverse environment in our hackerspace than the people who are originally there and their friends, or maybe people who are into information technologies, or we can just build a more inclusive and diverse skill set within our hackerspace, and then everyone benefits from that. And then, of course, who doesn't like exploring the world, right? It's just human nature to want to explore. So let's explore it with electrons. Why not? And then, of course, all of these together really make the world a better place. So one of the, building upon that, my passion for this project has to do with the fact that I firmly believe that every single person who walks in the door of the hackerspace has something that they can add to this project. I can't tell you how many times people walk in and I wish I was smart enough to build something like that. None of us are. Do I know what I'm doing? I don't know what I'm doing. I'm just gonna put that out there right now. I rarely know what I'm doing. I just do stuff, right? So it's like, some examples of things that people have to offer go from the highly technical, such as vacuum welding, the chamber needed welding. Circuit design is something that's somewhat technical. Not everybody can do circuit design. As the vacuum gauge circuitry, there's flyback, high voltage supplies, stuff like that. There's PCB fabrication, which is a little more, a little easier, but at the same time, it's nice to have that because at 2 in the morning when you have an epiphany and you just need 10,000 volts, sometimes you just can't wait for Seed Studio. 3D printing is something that I've tried to use because it's very quick. Also, you can sort of design something in CAD and 3D print it that night. People can come in. People come in and there's multiple people who know a lot more than 3D printing than I do that work with the project to build certain structures. CAD is very important because in one of the goals I have for this project is to release everything is open, just public domain. Just this is what we found, and maybe you can go one step further with it. So yes, we could stand all day in the back of the machine shop and sort of make stuff, but if we don't have CAD drawings, it's difficult to share that information with the world and to make it that better place that we're trying to. So CAD is very important to make a coherent set of information that can be shared with other communities and other people. And then, of course, machining is sort of inherent to vacuum technology. You have to machine the metal that makes up the chamber, mills and lathes. And machining is something that I never knew how to do. I am an electrical engineer. I don't know how to touch things that, like, if it's not hot glue and popsicle sticks, I don't know how to make it go. So I learned machining specifically from this project because I had to. And now I teach the lathing classes at the hackerspace. So now not only did I learn machining, but I get to teach other people how to do machining. That's very powerful. Laser cutting is something we can do. At the lab, we have a 100-watt CO2 laser, and we can use that to engrave and etch acrylic PC boards. But one of our members actually runs a metal shop, and he has access to a 5,000-watt laser, and we can cut armatures and pole pieces and stuff out of steel to wind the electromagnets. Here's a quadrupole core for the beamline. And then, this goes on forever. You could say, well, those are all very technical things. FPGA data acquisition, that's very technical. Human interface, a little less technical. Write some software for a tablet or a PC so that people can walk up and pinch zoom in on a sample. Well, that's cool, less technical. Beta testing. Hey, you, who are you? I don't know you, I don't care. Walk up, make it go. Find bugs, pinch zoom, rotate, do things that I wouldn't think of. There's also sample ideas. Kids come up. Can we put a marshmallow in the chamber? No, you can never put a marshmallow in the chamber, but maybe you could put a spider or a fly or something that I've never thought of, and we can look at it in the chamber. And then, all the way down to let's paint the chamber in purple flames. Why not, right? Everybody has something to offer this. Everybody has passion and energy to add to this project. So now about the project itself, a little more technical, a little less of my tears. The chamber itself we got used. It was kind of expensive at $400, but as none of us knew how to TIG weld or had access to a TIG welder, we thought it's a good place to start. The guy at this scrap yard had it. It's aluminum, which is not the best, but it'll work, right? So we got it, and we promptly filled it full of holes because it needed flanges. So we CNC milled using one of our members' home CNC mills. Holes in it, and we put the profile on the inside of these flanges so that they match the curvature of the outside and could be welded. And then another one of our friends has a TIG welder, and he knew somebody who was experienced at vacuum welding, so he very graciously welded the chamber for us. And then we leak checked it with alcohol. There I am with a spritzer bottle, endlessly spritzing the welds to find the leaks. I found that leak checking was very easy because the rubbing alcohol penetrates The rubbing alcohol is less viscous than water. It really gets into those tiny pinhole cracks and just instantly fills and spoils the vacuum. And then it has this funny habit of freezing. So actually the vacuum, after you spray a leak and it leaks, it actually gets a little better until the ice melts, and then it gets worse again, obviously. But it's a very nice way to check for leaks within the chamber. So here's just a calibration change where I adjusted the thermocouple gauge and then started spraying the chamber, found a bunch of leaks. They froze, the ice melted, then I sprayed them again, they started to freeze, turned off, and they got bored. Then fixing them, I actually went around with nitrocellulose lacquer. One of the resources that I found the most useful is outgassing.nasa.gov. You can put in any material you can think of, and it will tell you how good or a bad idea it is to put inside of a vacuum chamber. They have a low outgassing database, and then they have a general database. And it turns out that clear nail polish, which is nitrocellulose lacquer, does really well and is very low outgassing. And the contaminants that it does outgas do not recondense, so they don't spoil your chamber. They just kind of get evacuated. So this is a plot where I'm actually spraying and then painting, and you can see it gets better and better and better. And there was a massive leak I found, and then it just crashed. And after that, all the leaks have been sealed. A turbomolecular pump was donated, and while it's like, cool, yes, $10,000 worth of 90,000 RPM metal, great idea, it doesn't actually help other people achieve the goal of building an SEM. So while I would love to use this and will use it, I don't want to rely on it because it's not hackable. If it breaks, we're screwed. If somebody else says, can I build an SEM? It's like, do you have 10,000 bucks? So another thing you'll notice here is this is a conflat flange. And I do not love conflat flanges because you have to lathe the mating flanges out of stainless steel because they bite into a soft copper gasket. So I just turned a piece of Viton on the lathe, and guess what? You can machine a mating conflat flange out of aluminum and just squash Viton in there, and it works really well. So here it is hooked up to the chamber. There's the turbo pump, some valves, the dual vane rotary. Here's a chamber schematic because honestly it's difficult to see from a photo. So there's the chamber has a large door. There's a Bayard-Alpert gauge to measure high vacuum. There's the TC gauge to measure low vacuum. The beam column sits, I'll show it in the next picture, on top of the chamber. Turbo pump, roughing valves, roughing pump. It's a pretty simple, straightforward schematic of the vacuum system. Two types of electron guns that we've been working with are cold cathode electron gun, which works at about 5 to 50 to 100 millitorr, depending on the geometry. And I like that because you don't have to use the turbomolecular pump. You don't have to get to 10 to the minus 6 to make this work. Thermionic, on the other hand, you have to heat the tungsten filament over here up to several thousand degrees. It starts emitting electrons. And then you use this structure called the Vaynelt to only allow emission off of the tip, and you get this beam. The best thing about the thermionic is you can see that the entire electron beam is conserved and ends up going down the beam line, whereas the cold cathode one is you lose most of your electron beam because you're basically just putting a mask in front of it, but it does work, and it works in low vacuum conditions, which means it's hackable. And here's some, yeah, it broke, but it shows you the internal structure. There's a glass tube surrounding the a central high voltage, and then there's an aperture down here at the bottom with a tiny 0.3 millimeter hole in it. And then a plasma is struck inside, and you get, I'm gonna go forward actually. You get a beam. And to the left is after 8 inches, this is an unfocused beam, so you just see the exit aperture shape on, and this is a phosphor, so it's just being visually prototyped. And then I'm gonna go back and talk about the lenses. Electron optics are just like light optics. They use lenses, except they're electromagnetic instead of material property specific. So if you have a solenoidal field, you can focus the beams down to a dot. So here's the 2 halves of the solenoid. The small gap in the middle allows the field lines to protrude into the beam line at one very specific point so that they're all bent on a single plane, which reduces aberrations. In between them is a 1 millimeter thick brass washer to allow spacing but not interfere with the magnetic field lines. The whole thing's made out of 1018 steel. That goes coaxial. Then there's a deflection quadrupole, which is 3D printed to do the rasterization pattern. Here's an alignment quadrupole, which is laser cut. I don't know which one's better for which task. I'm still working on figuring out which one works better. One of the things that the alignment quadrupole was kind of cool because this material is not really meant for electromagnets. The hysteresis is awful. And so you can actually align it and then turn off the coils, and guess what? It stays aligned. It's kind of cool. You can kind of push it around the magnetic hysteresis, and okay, it's good. And then it doesn't get hot, and you don't have to turn on the power supply. Here's a picture of the full beamline. At the top is the cold cathode electron gun, followed by the solenoid, an alignment quadrupole, a deflection quadrupole, and at the bottom is a small plate covered in phosphor. And by phosphor, I mean I took a CFL, like light bulb, and broke it, and kind of put the powder on a plate. Totally hacked. So you can see that this is 3D printed lens carriers, and then the laser cut. The top is a laser cut acrylic plate to push down on the O-ring so that it compresses. And currently that's where the SEM is at. It's not completed, but it's very much a work in progress. There's a high voltage power supplies and lens drivers are built. So right now it's more about characterizing and prototyping the optical system, but the next step is really to get the signal, to put a sawtooth wave into the deflection coils, rasterize the image, and then either look at sample current, which will be a very gnarly, gross, but still coherent data, or look at backscatter, which means putting more sensors inside of the chamber. So that's really the next step. And are there any questions?
Questions for the second part?
How difficult is it to focus the beam very, very narrowly? Because that's, I mean, the focal point is one of the main characteristics of it.
I don't have any measurements, but other than just visualization, you can see that it's, I would guess, it's difficult to tell if the phosphor is really responding to the beam or if the phosphor is exciting more phosphor and you're getting splash. But, you know, you could say it's about 0.2 millimeters. That's not, you know, a research grade microscope, but that's enough to make a penny look round. And so you can add, and this is a single lens design, it's a very low precision lens. So by adding multiple lenses, you can defocus the previous, you can demagnify the previous crossover. So if this spot's 0.2 and you put another lens, well, you can defocus that by another, you know, 100 times and you can get 0.02, and then you can put another lens in and defocus that. And aberrations become introduced and become limiting, so you need quadrupoles and hexapoles to squish the beam back round. But, you know, like I said, once you've got a penny that's round, you've got proof of concept, and now you can incrementally build up and you can say, well, you know, a penny is round and that's fine. Now we can actually make the cables not go everywhere and kill people with high voltage first before we start to really, you know, make this a research grade, which, you know, the goal is never to make it research grade, it's to inspire people, so.
Mike should be on, so. There's one question back there and then here in front.
Well, we just had a question about a lot of high voltage electron beams hitting metal targets and X-rays being generated.
So the accelerating voltage is 10,000 volts, but there's actually quite a lot of voltage dropped, and that's really the next step is I need to measure the resistance of the plasma. Some of the voltage is dropped across the plasma, and so the resulting beam is not 10 keV because you have a drop. And so I would guess from the arcing that I've seen and stuff, 5,000 electron volts. That's not enough to generate X-rays that are going to make it through the glass. But somebody did suggest, well, you should probably keep a Geiger counter to sort of hang on. That's not a bad idea.
What electron gun are you using right now, and what electron gun do you plan on using in the future?
Right now it's just the cold cathode, but I would like to make 2 beamlines on either side of the chamber, one thermionic, which will only be switched on under very deep vacuum conditions, and then I'd like to keep the cold cathode because it's hackable, and but the optics are the same. It doesn't make a difference. The optical train will not be different, so you literally could have, you know, swappable, you'd have to break the vacuum, but swappable guns that you could put in and out, and one's very high resolution thermionic and one's very, you know, lower resolution cold cathode. And because the vacuum level is very, you know, high pressure at 1 to 50 millitorr, the resolution is going to be spoiled by the, you know, the pesky air molecules that get in there. The mean free path of the secondary electrons is going to be nothing, but you're going to ionize air and you can actually detect the ionization of the air. so you can accelerate, ionized air. And there's a trade-off with the different types of guns, but I'd really like to stick mostly with the cold cathode because it's the one that's hackable and it's the one that we can share and other people can, experiment with without coming up with $10,000.
Or in the back.
It would be really interesting to hear the following thing about the hackerspace itself, or at least about your implementation. Do you have some safety policy?
I guess don't kill yourself or others?
Yeah,
So some regulations on that topic.
We kind of have a policy of don't be a dick. So if you're gonna, play with 50,000 volts, don't make it so that other people can't do their thing. But as far as safety, we will stop somebody if they're being careless. If somebody's just starting fires in the lab, right, that's not really okay. But if somebody kind of is taking precautions, they know what they're doing, it's really is a gray area because we want people to do their projects, but we really don't want someone to die. So it's something we've battled with a lot, actually.
And to follow up.
Yes, I just wanted to ask that from the point of view of the balance between keeping enough freedom and creativity and, as some amount of people are working together in some closed space, you should take some measures.
Well, and that's true. We are a community, first of all, right?
So thank you for your answer.
Yeah, we are a community, and so if we're doing something that impacts the community in a negative way, you should stop because it's a community, first of all. And if people feel like you're being unsafe and they don't feel safe around it, then there needs to be a discussion. The person should not just be able to come in and be reckless and say, I know what I'm doing, just go away. I mean, there needs to be a discussion. It is a community. There needs to be that sense of safety. And so if it was kind of a joke, there's high voltage everywhere. I do not keep the high voltage on when I'm not at the SCM working. And the high voltage cables are all routed behind, so there's no way anybody could, accidentally come into contact with them. But it's a good point, right? If somebody's literally leaving high voltage capacitors charged around the lab, that's not okay. And freedom is good, but not when you're killing people, right?
Hello, Jasper. Thank you for that wonderful speech. I came in a little late, so I caught all of that one and part of the first, but thank you very much. And I'm loving Exceptionally Hard and Soft Meetup also. Thanks, Sebastian, and all the crew. I don't think I met you, but what are your plans for preparing targets once you're finished with the scope? Are you going to build a sputterer?
Baby steps, right? I'll probably build an evaporation system first because it's easier. If somebody wants to, come in and make a sputter coder, I will not turn them away. But that sounds like a project that I probably won't.
Do you know how? Do you know how to do it?
Well, right. I mean, you accelerate ions into a target and they sputter, but it just means building a whole nother vacuum system and coming up with. I just feel like I'd be more dedicated to the SCM itself, but it's certainly not. I mean, if I need it, I need it, right? The other thing is, I forgot to mention with the high pressure system, there's so many air molecules that sample charging is not as big of a problem because the electrons can bleed off into the air. So actually the higher pressure cold cathode gun allows you to image non-conductive samples better. You still have sample charging, which is a problem, but the samples will bleed away. So if you rasterize them slowly enough with a low enough energy beam, you can actually do sampling of insulative samples.
So do we have more questions? It's not the case. Thank you very much.